Hello guys, welcome back. In today's lecture, we'll look at a few more examples on left recursion. So, I hope you all remember what is left recursion. So, when a production looks like this, when LHS and RHS have the same non-terminal, when the RHS has the same non-terminal as LHS on the left extreme, it is called as left recursion. So, why is it a problem? When there is left recursion, the parsers get into infinite loop. So it is necessary to remove this left recursion, and I had also told you how to remove this left recursion. This is the technique. These are the two steps that we follow to remove the left recursion in any production. So today we'll look at some more examples on left recursion. So here we have a production grammar. So as you can see, the first production has no problem. There is no left recursion in this first production, but there is in the second production. So we have same non-terminals here, as you can see. So this we can consider as alpha and this as beta. So how do we solve this? This can be solved this way. L produces S L dash, and L dash in turn produces comma S, that is alpha, and then L dash epsilon. Okay, so let's solve one more example. So in these three production, where can we see left recursion? We have left recursion in the first production and in the second production. So let's consider this separately. Let's consider this first. So in this case, this is the alpha, this is the beta. So E produces TE dash, E dash produces plus TE dash epsilon. Now let's consider the second production, T star F. So in this is the alpha, this is the beta. So T Ft dash, T dash star Ft dash epsilon. And the last production will be written as it is, since there is no left recursion. So this is about left recursion. I hope you all have understood left recursion properly. Now let's discuss what is left factoring, why is it a problem, and then how to solve this left factoring problem. So before understanding what is left factoring, let's try to understand backtracking. Okay, and what exactly is backtracking. So if there is any production like this, A producing A alpha 1, A alpha 2 and A alpha 3. So before that, top down parsers are mostly predictive parsers. They use the technique of predictive parsing. So when top down parser sees this particular production, okay, let's assume our input string is A alpha 3. Okay, our input string is A alpha 3. So when parser sees this production and sees this input string, so what the parser does is it will first consider this particular production A alpha 1. Okay, so what it does is it tries to generate the parse tree A alpha 1, but once it realizes alpha 1 doesn't match with alpha 3, it backtracks. Okay, and then it goes to the second particular production. Then it uses the production A alpha 2. Again it gets to know that this alpha 2 is not matching alpha 3, so again it backtracks. So then it makes use of the third production, A alpha 3, where this is matching the input string A alpha 3. So due to this backtracking, the efficiency of the parser comes down, right? Because there are common factors in all these inputs. See, as you can see, there is same common factor, that is A. Due to this, there occurs backtracking and it reduces the efficiency of the parser. So what do we have to do? So this problem where all the some of the production has same string, right? So this problem is called as left factoring. Okay, so what is the solution for this? The simple solution for this is to remove the left factoring. So how do you define left factoring? Left factoring is grammar transformation for producing grammar suitable for predictive parsing. So what we are going to do? We are going to transform grammars like this. So you have to transform the grammars which have left factoring to the grammar which do not have left factoring. It is like this simple maths equation, as you can see. So what is the common factor here that you can see? 2, and you remove it and it becomes 2 into x plus 2. So this solution, removing of left factoring, is as simple as removing this common factor from this equation. So let's see how to remove this left factoring first. So we have these productions, A producing alpha beta 1, alpha beta 2, alpha beta 3 till alpha beta n. As you can see, all the productions has this common factor of alpha. Now it's our task to remove this left factoring. So as I said, you have to first remove the common factor. So how do we remove it? I write A producing, let's remove the common factor first. So I will remove the common factor alpha, and instead of beta 1, beta 2, beta 3, I will write as A dash. Okay, I'll write it as A dash. Then with A dash, I will produce all the remaining productions. Okay, all the beta part, I'll write it in the second production. So this is how you remove left factoring. So this is as simple as that. Now let's look at few of the examples on removal of left factoring. Okay, here it is an example of the production which has left factoring. So what does left factoring mean? Left factoring, these are the productions which have common prefixes on the RHS. Okay, so since the decision is done seeing the prefix in predictive parsers, this becomes the problem. So hence we have to do the removal of left factoring. So as you can see here, the common prefixes in this particular productions are IETS, right? So how do we remove it? So S producing IETS and then S dash. Okay, and then S dash producing, since we don't have anything here after this S dash, this will give rise to epsilon and then ES. Okay, and there is no left factoring problem here. Let's look at the second example. So in this grammar, there is no problem with the first two productions, and we can see common prefixes here, which is ID. How do we remove it? List ID, list dash, and then list dash giving rise to comma list epsilon. So this is the solution for the second grammar. Now that you all have understood what could cause problems in parsers and how to resolve them, let's continue our discussion. Yesterday we had discussed about types of parsers, and I had told you there are two types of parsers. Those are top-down parsers and bottom-up parsers. So let's first discuss about top-down parsers. As the name indicates, top-down parsers constructs the parse tree from the root of the tree to the terminals, that is the leaf nodes. Okay, whereas the bottom-up parsers starts from the leaf nodes and it ends to the root node, whereas in top-down parsers the parsing starts from the top, that is the root of the parse tree, to the leaf nodes of the parsers. Okay, so I have an example here. Okay, so these are the productions, and at each step in the derivation I'll have to make two decisions: what production will I replace and what non-terminal will I replace. So these are the two decisions that I have to make during the top-down parsing. Okay, so why do we prefer top-down parsers? Top-down parsers are more efficient because the construction starts from the root node. Okay, and okay, that's about the top-down parser. And here we have an example. So this is the grammar that we have for the declaration of identifiers. We have D producing type list, type producing int, type producing float, and list producing id comma list, and then list has id. So this is the grammar that we have specified for constructing for the declaration of any identifier. So let's see the example. So if our input is int xy, how exactly the top-down parser works on this particular grammar? So first, as the top-down parser, it will always consider the start symbol. So the start symbol in our grammar here is D. So it will always start with the start symbol. So for this particular input int xy, our parse tree starts with the input string D, producing type list semicolon, and then from this we have type list and then semicolon. Somewhat I guess you are able to make the relevance here. This is the type, this is the list, and then we have semicolon. Okay, now since this is the top-down parser, the top-down parser does the leftmost derivation. That means I'll have to first replace this leftmost non-terminal first. So let's see what options do I have for this leftmost non-terminal. So the leftmost non-terminal that I had is type. So for this type I have two options, that is type producing int and type producing float. Since our input is int xy, I will consider this first production for type, and I will replace this type with my int. Okay, so we have reached the terminal, so we will move on to the next non-terminal, that is list. We are done with the first leftmost thing here, leftmost prefix. So I'll come to list here. This is the next leftmost non-terminal that I have to replace with. Now let's see what options do I have to replace the list. So for list I have two options, list id comma list and then list id. So if you see the input here, I have x comma y. So I just cannot make the decision of replacing list with id because I need two identifiers there. So I will choose list id comma list. So the list will be replaced, this list will be replaced with id comma list. Okay, now we have arrived at this terminal. Now the leftmost non-terminal that I have is this particular list. Since I just have one more identifier left here, y, so I will replace this with id. So this is how a top-down parser works. Okay, it starts with the start symbol of the production, and at every step it makes the decision on two things: which non-terminal will I choose. Since this is the top-down parsing, it will always choose the leftmost non-terminal to replace, and once I have chosen the non-terminal that I have to replace with, for that particular non-terminal, which production will I choose. For example, I chose type here to be replaced. For this particular type, which production will I choose? This I will choose, or this I will choose. So for every replacing that you do, you have to take decision on two things. I hope you have all understood how top-down parser works. Let's see another example of how top-down parser works. I have a grammar here where I have two productions: S producing ICTS, ICTS-ES and A. Okay, so here the ICTS stands for if condition then statement, then if condition then statement, else statement, and this is some variable A, and then C for condition we have some binary equation. And let's assume that our input is IBT AEA. Okay, it stands for if binary condition then A, else A. Okay, so we have to arrive at this particular instruction using this grammar that we have. So at every statement we have to make some decisions. Okay, so since this is top-down parser, it will choose the start symbol as the first symbol. So start symbol is S. From S I will choose ICTS. Okay, and then this C I will replace with B, so this becomes IBTS, and then I will replace this S with this production ICTS ES. So my instruction now will look like IBT as it is from the above production. This S I have replaced with this particular production, so this whole thing is replaced with ICTS ES. Okay, so now I have all the terminals here. So the next thing that I have to replace is this particular C. Since these are all terminals, what I will choose? I will choose again this production C with B, and then till here I have all the non-terminals, the first terminals. So the next non-terminal that I have to replace is this S. So this S, let's look at the input string. What do I need next? A. So I will replace this A with this S with A here. So it looks like this. Then I have all the terminals still here. So the last and next non-terminal that I have to replace is this S. This S is replaced with A here. So this is how the top-down parser works. It does the leftmost derivation from left to right. It starts replacing everything like here and then this and till the end, till we reach at the input. And if we don't arrive at the input, it means there is some error in the input.